Okay, the quiz on rules of inference, but this time we were dealing with quantified statements. And so again, we go to our apartment building. It might be a different apartment building, but the new thing is once more that we have everything ranges here. X here, the variable x, I'll point it out here, the variable x is ranges over the tenants in this building. So again, we're making general statements not about a particular person in this building, but by any person in this building. Okay, and so I told you to use these predicates, so it makes it a little bit easier. So let's rewrite now all the statements using the given predicates. The first one says all tenants live in a studio except those on the second floor. Now that's perhaps something you had a little bit problem with. Remember, this live in a studio, that would be S, right? So this would be S, and second floor, that would be P. So it has to do something with S and P. It is also universal. So let's, at least that's out of question for all X. And so what now? All tenants live in the floor except those on the second floor. So let's try to slightly reformulate this. I would say, okay, if you live on the second floor, then you don't live in a studio. Or, wait, no. This says that except those on the second floor. So it says, if you're on the second floor, then you don't need to live in a studio. Okay? So that means that if you do not live on the second floor, then you must live in a studio. Right? All tenants live in a studio except those on the second floor. So if you're not on the second floor, you live in a studio. Right? This was one option. The other option was, if you live on the second floor, then then what? You might live in the studio or you might not. This doesn't say that. It says all tenants live in the studio except those on the second floor. But there might very well be studios on the second floor as well. That's not excluded by this statement. So the right thing is that if you're not on the second floor, so not PX, then for sure you must live in the studio. Okay, the second one. Everyone from the second floor has paid his month's rent. That is much easier. If you're on the second floor, that was SX, right? No, that was PX, sorry. PX, then you paid your rent as R of X. Some tenant has not paid his rent yet. So that's an existential statement. There is an X, not Rx. And this is all that has been said. And now what you need to show is there is some tenant who has not, that lives in a studio and has not paid his rent. That's what we need to show. So perhaps what we will say, we have to show there is an X who lives in a studio. Now again, in English there is no and here, but that is the relative clause who makes it an and. What you really means is there is a tenant, he lives in a studio and he has not paid his rent. And, not Rx. So that's what we want to show. Again, let me make it nicely colored that you see where we're going. Good. So if this is what we're going, well, okay, what we have here, luckily there's not so much. And I hope from the review it's become clear that what the first thing one should try to do is use statements like this here, because they give direct information, at least when you use existential instantiation. Because for instantial instantiation, there is a tenant, let's call the tenant T, just so that you don't always think it has to be A. So T is the name of some tenant, or the apartment number of that tenant. But again, we don't actually know, but we know this, not RT. Okay, so now I have the negation of R, and R only really occurs in this statement as a hypothesis. Therefore, since I know it's not true, I'm going to want to use modus tollens, right? But in order to do that, I have to prepare this statement. So let me copy the statement 2 again for all X, Px. Rx. I have to kind of make it into a propositional statement, and I do that by what is called a universal instantiation. meaning I'm going to take X to be that particular tenant T, and that means that this particular tenant P, if PT, then RT. Oh, but what I just said is this here, not RT. Right? I'm just have this truth now, and therefore I can conclude by modus tollens. Since the hypothesis is not true, the conclusion could not have been true. So this is what I know about T, not P, T. Okay, not PT. Can I use this? Well, let's see. What else do I have? I haven't used 1 yet, so let's go to 1. 1 says for all x, not px, then s of x. I want to do this for this particular t. Can I do this? Yes, because I have the principle of universal, or the rule of inference, universal instantiation, where I'm going to again take x equals t. So I know that not pt, then st. Okay, great. So now that I have this, I can use the fact that not pt, because remember that I just already proved, to just do a regular modus ponens and conclude st. Now let's see where we're going. We want an x, as x, and not rx. Okay, as x, that's good because that's what I have here, so I'm going to make this already green. That seems to be fitting. What about not r? Oh, okay, but I also actually have this. So now we have something that it doesn't really need a name, but let me just copy it here. The fact if you have two truths, then you can put them together, and this is what we call conjunction. So we have st and not rt. And this, so there is a t, this particular tenant, whom we don't know exactly who that is, but there is some guy or girl that satisfies this, so st and not rt, and therefore we can do existential generalization. So existential generalization says if you have predicates, and in these predicates you have filled in always the same value for the variable, then you can say there is an x, sx, and not rx, and that's exactly what we wanted. Okay, so that was the great.